Hi everybody. Hope everybody's having a good day today so far. What we're going to do here is we're going to talk about the geometry and the algebra of Rn, or a Euclidean space. And you can see that I've already drawn a pair of axes up here. So we're going to be doing some examples in R2 so that this is the appropriate picture here. And so we're going to be dealing with n-tuples. We're going to be dealing with elements of Rn, or in fact, we're going to be dealing basically, to begin with, elements of R2. So they're going to be n-tuples, or lists, as we've said. And we're also going to use, we're going to say they're points, or they're vectors. So here I've added two more words that we can use to refer to these, and these are just synonyms for one another. And when we use points or vectors as the descriptor, as the word that we're using to describe this, that's because we're thinking of Rn. We're thinking of Euclidean space, for example. So this is a situation where the elements of the set from which we take n-tuples are numbers. So for example, when we had the real numbers and the rational numbers and the natural numbers over here in a previous lecture, there we were talking about numbers, and if we took n-tuples, we were talking about n-tuples of numbers, and there we use the terms often points or vectors to describe n-tuples or lists. And so let's look at several examples here. Let's take a point, an n-tuple, an ordered pair, because here we're going to be doing everything with n equals 2 to start with. And so that's going to be a pair of numbers. And let's let that be the ordered pair 3, 1. So that's going to be 3 in the x1 direction, 1 in the x2 direction. So that's going to be there. And let's just label that x. And in fact, I'm going to call this x bar. And I'm doing that because I'm going to put another point in the picture here, and I'll call that x. So that's going to be x1, x2, and I put the bar on here just to distinguish the two from one another. And let's let this be, let's let x be 4, 3. So that's going to be over here at 4, up here at 3. So that's going to be about, let's say, here. And so what I want to do, and this is of course x. What I want to do is I want to be able to talk, for example, about moving from x bar to x. X bar here was 3, 1. I want to talk about moving from x bar to x, and so I'm going to refer to this movement from one vector to another as delta x. And so the delta x here, first of all, let's notice that, let's write down over here, delta x clearly has two components, just like x bar and x. It has two components because I've moved one unit to the right, and I've from 3 up to 4, and I've moved 2 units vertically from 1 up to 3, from 1 up to 3. And so this has two components, and they are 1, 2. So let's actually write that over here. We have delta x is, and I'm going to write, since there's two components, I'm going to write the two components separately, and that is 1, 2. But you'll also notice that if this is 1, 2, well, 1, 2 is actually that point right there. That's the point 1, 2. And so I could draw the same kind of arrow going from the origin, in this case, the 0 vector. And in fact, let's just point out that that vector there is, and I'm going to use this notation, a 0 with a line under it, to represent the 0 vector, also called the origin, in this case the origin of R2. And so this is the vector delta x also. 1, 2, it's this vector here. So you can say, well, these look the same, and actually they don't look like they're exactly the same length, and that's just because I didn't draw them carefully enough, but this is supposed to be the same length as this. And so they look the same because they really are the same vector. All that's happened here is I've picked up this vector and moved it here. I've moved the 0 vector part, the tail to here, and the head to here, so it's really the same vector. And so let's also notice then that I could regard delta x as the vector x minus x bar. And in fact, we could write this as 4, 3 minus 1, 2, minus 3, 1, let's get that right, minus 3, 1, equals 1, 2. And so you can see that what we've done here is pretty much what I said I was doing over here, but here I've actually written this as if I've got two vectors and I've got one vector subtracted from the other vector to give me this. And the subtraction was done as I described over here. The first component of the difference vector is 1, which is 4 minus 3, the difference of the first components, and the second component is 2, the difference of the second components. So what you could say that we've done here is, I haven't really written this down as a formal definition, but this is basically subtraction of vectors defined component-wise. We could call it component-wise. I get the first component of the difference vector by taking the difference of the first components, and the second, the difference of the second components. And so let's also notice, of course, that we could represent x as x bar plus delta x. And of course, I'm using an x bar and a delta x and an x here because this particular kind of notation, this idea of x being some base vector, some benchmark or starting vector, and then we move by this amount to get here, that is, of course, going to show up quite a bit. That should be kind of familiar from when you're talking about the definition, for example, of a derivative. And so here I would say that x is x bar, which is 3 and 1, plus delta x, which was 1, 2, which gives me 4, 3, the vector x over here. And of course, geometrically, what this is we could say that this, we could write this as the vector x bar. So now I've got x bar as a point, but I've also got x bar as the vector or the movement from the 0 vector out to that point. And so I could think of x here as x bar going out here, and then adding delta x to get out to x, and that's what this says here. But of course, I could just as well say that this is delta x plus x bar, and that would be starting with delta x and then adding the vector x bar, so this is also x bar, and I get to the same place, of course. So this is just saying that it doesn't really matter whether I add the vectors in this order or I add the vectors in this order. The concept of adding vectors, we would say it's commutative. And we don't really use that term very much, but the idea is that it has this commutative property. It doesn't matter what order we do things in, we do this operation in, we get the same thing either way. And of course, this parallelogram is often used to describe what's going on in this commutativity, that vector or addition of points or n-tuples or vectors is commutative. The order doesn't matter. And so let's write in here that what I've done is I've said I haven't really defined addition here, but I have added these vectors, and we're now going to go to a formal definition. Addition of vectors is also done component-wise. I took 3 and 1, the two first components, added them to get 4, 1 and 2, added them to get 3. So what we want to do now is actually write down a formal definition of adding vectors and, of course, multiplying vectors by numbers too. And in fact, let me even do that over here very kind of quickly. Let's say we could take a lambda, which is a real number, and we could then take that lambda and multiply it times, and let me multiply it times delta x, since on the picture that's going to work a little better. So no, I'll take it as lambda times x. So lambda times x is, of course, lambda times x1, x2. And that is then going to be, if we define multiplication by a scalar component-wise, then that's going to be lambda x1, lambda times the first component is the first component, and lambda x2, lambda times the second component is the second component. And so scalar multiplication, so this is scalar multiplication of a vector, multiplying a vector by a scalar, is defined also, although we haven't written down a definition yet, component-wise. And of course, visually, what we're going to get is that this is now, this is the point x, this is also called a vector, but it's called a vector because we sometimes use the kind of an arrow like this. And so this would be approximately 2x, where lambda is 2. So this would be, in this case, if it's 2x, this would be 8 and 6, for example. So it's clear that what we did here with subtraction, and perhaps more important, addition and scalar multiplication of vectors, when n is 2, everything we did, we can do for any n. We just do exactly the same for any n at all. And so what we're going to do now is we're going to take these off. We're going to give a formal definition of addition of vectors, multiplying a vector by a scalar, and then we're going to develop some of the properties of those two operations. So that's what we'll do next, but we'll first have to take these off to get some more space to work with. So that's what we'll do next. Okay, now we've got some space to work with, and so let's now write down a formal definition of vector addition and scalar multiplication. So I just use this abbreviation, DEFN, for definition. And so addition scalar multiplication of vectors, let's say vectors in Rn, are defined component-wise, as we've said. And so, formally, we say for all pairs of vectors x and y in Rn, x plus y is equal to x1 plus y1, x2 plus y2, whoop, let's get that y, not x, xn plus yn. And I guess you could say, well, what are the x1s and the y1s and so on? And of course, since we have vectors x and y that are in Rn, of course, it is the case that x has to be of the form x1 to xn and y of the form y1 to yn. That's implicit in the fact that x and y are vectors in Rn. That's how we've defined elements of Rn in terms of these components. And for all vectors in Rn and lambdas, real numbers, this should be Rn and this should be R, we have lambda times x is defined to be lambda x1 to lambda xn. So this is exactly what we had done on the screen before we took it off for just R2. So all we're doing now is doing it in general for n and kind of doing it as a formal, specific, explicit definition. We now would like to develop some of the features, some of the properties that these two operations have, and that's what we have here. So here we have our first, I think it's our first theorem, and this theorem tells us 8 of the properties that these two operations have in any, for Rn, for any n, and I've labeled them V1, V2, down to V8 here. And I've used V because these are properties of these two operations on vectors. And so V for vectors here, but also V because we are ultimately, shortly, maybe 1 or 2 lectures down the road, going to be generalizing our ideas here to vector spaces. I'll say a little more about that in a few minutes. So here we have these, I've said that these are 8 properties that vector addition and scalar multiplication have. And so let's actually look at the properties in just a little more detail. And so actually all of them are trivial to prove from the definition here, from the fact that we've defined vector addition component-wise and that we've defined scalar multiplication component-wise. So let's first just look at the first 2 properties, V1 and V2. So V1 here says that if I take any 2 vectors and I add them together according to this definition, what I get as a result is itself also a vector. And of course, that's clear from this definition. If I take 2 vectors and I do this, then the first component is a number because x1 and y1 are numbers and we've added them together. The second component is a number. It's a number in R. It's an element of R. The last component is an element of R because I've added together 2 elements of R. So what I get is an ordered n-tuple of elements of R. So indeed, trivial to see, to prove that from the definition we can see that when I add two vectors together, I get a vector. We say that we describe that by saying that the set Rn is closed under the operation of vector addition. Closed under the operation, meaning that if we perform that operation on elements of Rn, on vectors, we get back something that's still in Rn. The second property, same thing for scalar multiplication. So it says that Rn is closed under scalar multiplication, meaning if we take any vector in Rn and any scalar and multiply scalar times a vector, what we get back is a vector in Rn. And of course, that's the case. If I take a vector, x1 to xn here, and I do the scalar multiplication, and I define it component-wise, that's a number, that's a number, that's a number, that's a number. They're all real numbers. So this is in Rn, and maybe I should even emphasize this by pointing out that this is in Rn, and this is in Rn, which is just V1 and V2. So those are the first two properties, trivial from the definition. You just follow straight from the definition. Let's look at now the properties V3, V4, and V5, and then I'll say something about V6 as well in a moment. So V3, V4, and V5 are also properties of these operations that are trivial to prove from the definition. Let's look at V3 first of all. V3 says it doesn't matter whether I take the vector x and add y, or take the vector y and add x. I can do it in either order, just like what we saw in our example earlier with adding x plus delta x to get, or x bar plus delta x to get x. The order didn't matter. And this says the order doesn't matter. And that, of course, follows immediately because x plus y is this, and y plus x is this, with the order of addition of the real numbers reversed. And, of course, addition of real numbers is commutative. The order doesn't matter. So this and y1 plus x1, y2 plus x2, yn plus x2n are clearly the same n-tuple, the same vector, and that's what V3 says. So the same thing is true for V4 and V5. We do the same thing. We can take the definition of vector addition and scalar multiplication component-wise and immediately prove V4 and V5. V6 simply says that the scalar 1 times any vector x is that same vector x. It doesn't change. It's kind of a multiplicative identity. And again, clearly true from the definition. If lambda is 1, then I've got 1 times x1, 1 times x2, 1 times xn, which is x1 to xn, x. So V6, again, it's immediate from the definition. And so now, finally, let's look at V7 and V8. Those are a little different because both V7 and V8 have in them the existential quantifier, not just the universal quantifier that's in here for all of the other properties. And of course, that universal quantifier is just the same as saying for every one of these, for all of these. The existential quantifier here in V7 and V8 is a little different. So V7 says that there exists some vector in Rn that I've labeled x hat, which, if you add it to any other vector, that what you get is the vector that you added it to. That is, you can add x hat, that specific vector x hat, to any vector and it won't change the vector. So I could add that vector to, we'll recall that we had earlier, we had a vector 2, 5, and 2. The prices of, I think it was milk, wine, and gas, or maybe it was gas and wine, I don't remember. And so this says that if I add to that the vector, in this case, I've said there's an x hat. That's clearly the x hat. So this is that vector x hat, which, if I add it to any other vector, I get the same vector. And it's clear that that's true for the 0 vector. It's clear that that's true for the 0 vector, again, directly from the definition. If I add 2 plus x1 plus 0, x2 plus 0, x3 plus 0, or, as V7 says in the other order, 0 plus y1, 0 plus y2, 0 plus yn, I don't change the vector that I'm adding the 0 vector onto. So V7 is clearly true, and the x hat is the 0 vector. And V8 says that for every vector in Rn, there is another vector, x prime, which if I add it to the first vector, I get the 0 vector. And of course, it's obviously the case that the x prime, if I start with a vector x, the x prime that I want to use to add on to x to get the 0 vector, that's minus x, which is minus 1 times x, which V6 says is, whoops, there should be a minus 1 in there, which V6 says is minus x1 out to minus xn. And if I add that to x itself, I'm going to get, if I add that to x, so if I take x plus x prime, it's clear that the first component is x, the first component is x minus x1, x1 minus x1. Second component is x2 minus x2. Last component's xn minus xn, so all the components are 0. And I've got the 0 vector, exactly what V8 says is going to happen. So all 8 properties are simple, trivial consequences of the way we defined vector addition and scalar multiplication. Now let's just finish off here by saying, first of all, this is so simple, so trivial, you could say, that does it really merit us spending whatever it was, 10 or 15 minutes doing this? Does it merit calling it a theorem and actually saying that we're doing a proof, we're proving each of these things? Well, it really is that trivial, there's no question about it. But it actually is very worthwhile to write it down formally, to kind of even do the exercise of carrying out these simple little proofs, but to write it down formally so that we have these 8 properties. And the reason that that's so important, and believe me it is that we are going to see many, many situations where we have some kind of a context, some kind of a situation, say a mathematical situation, where it is natural to define an addition concept and a multiplication by real numbers concept. And those 2 operations that we define have all the same properties as here, but they aren't Rn. They're some other kind of a set. And the operations aren't just adding up real numbers, component-wise like this. They could be quite different, but if we can identify in the set we're working with, typically not Rn, if we can identify some operations that are important and useful, and if those operations have these 8 properties, then we can do everything that we do with addition and scalar multiplication in Rn, we can do in that new context too, and that is extremely powerful. So I'll say this a different way. We are going to generalize this theorem, and I'm going to call it elevate it, to a definition of vector space, and then we are going to see lots of situations that are vector spaces. They run throughout economics. They're going to run throughout this course, throughout Math Camp, and they are going to build on just this simple idea and this simple idea over here. So that's it for this lecture. See you all next time.